All right, in this video I'm going to talk a little bit about angular momentum. Angular momentum is the measure that we have of rotation. And I'm going to put rotation in quotes here because what we're really talking about is rotation about a point. And so our first example of this is going to be curious to you because it's not going to look like something is rotating at all. In fact, we have a location here, A, and you have an object that's moving past it with a momentum p. So there's a vector which points from that location A to that object, and we'll call that RA. Now, it doesn't look like this thing is rotating about this point, but it turns out it has angular momentum. It is, in some sense, rotating. It's changing its angular momentum. Well, it's not changing its angular momentum with respect to this point, but it has angular momentum with respect to this point. So the angular momentum that we are defining is the vector product of this location vector and this momentum vector. So this object will have angular momentum about any point that is not along the line that the object is moving on. Because as a property of these vector products, these two vectors, if they are parallel or anti-parallel to each other, they produce no cross product. There is no component, as we talked about with torque, there's no component of one of these which is perpendicular to the other. And so you will end up with no magnitude for your angular momentum. So as long as we're off of the axis here somewhere, we're going to get some component. Now, the details of how to calculate this are given in the notes, but I want to talk to you about the magnitude of this thing a little bit. So as we did with torque, what we're going to do is we're going to consider the magnitude first, and we're going to shift things around a little bit. So we're going to have a momentum vector here. We're going to move the location vector up, as I said we can do when we are trying to calculate these things. We're allowed to move the tails around, and there's an angle theta. And as we talked about with torque, we end up with a very similar result in that the magnitude of this is the magnitude of the location vector times the magnitude of the momentum vector times the sine of the angle between them. And this is just like we saw with torque, except now we have different vectors that we're paying attention to. Instead of the force vector, we're paying attention to the momentum vector. Now, what you can see here is that we want to maybe apply the same kind of ideas that we did from torque, which is what are we going to do with this sine of theta? Well, a nice thing to do is to apply it to the r vector, because if we take the magnitude of this vector times the sine of theta, we get precisely the perpendicular component of that vector. And so, just as before, another way to think about this is to multiply the location vector, which is perpendicular to p, times p, to calculate that magnitude. Now you can see from here, again, if these things are along a line, so that you're looking at a location, we'll call it B, that is along this line, there is no such perpendicular component of the r vector. In fact, the angle theta is 0, and so the sine is going to be 0. So there is no magnitude of the angular momentum along the line that an object will travel. There is no angular momentum associated with that. Now, this angular momentum, as we've defined it, is the definition of angular momentum. We often will think of it as the translational angular momentum. And we'll talk about that in a minute when we move into talking about rotational angular momentum. It's translational because it has to do with the translation or the motion of this object along a line, and not with the collective behavior of atoms around a point, which is what we'll get to in a moment. Now, the last thing to talk about here is the idea of what is the direction of the angular momentum. And just like we had with torque, I'm going to go ahead and erase this, and we're going to go back and draw the picture again. Just like we had with torque, if you are calculating the cross product of this r vector and this momentum vector to calculate the angular momentum vector, the cross product provides a resultant which is perpendicular to the other two vectors that you are calculating the cross product from. And so all the stuff that we're going to be doing is in the plane like this. And so the angular momentum vector will again be out of the page or into the page. But now we have a slightly different situation. We're going to pay attention to r and curl our fingers into p to calculate the angular momentum. Excuse me. So what we'll do is we'll point our fingers in the direction of the location vector, we'll curl our fingers towards P as we did before, and we'll find that the angular momentum points into the board as we learned how to indicate in the previous video with an X, because we're paying attention to the fletchings of the arrow which point into the board. So the angular momentum in this case is into the page. So this idea of the right-hand rule is quite useful when thinking about both torques and angular momentums, or anytime you have this sort of cross-product issue that you're dealing with, you can use the right-hand rule to deal with that. And again, as a reminder, it's pointing your fingers in the direction of the first vector, curling them towards, through the smallest angle, to the second vector, and your thumb gives you the direction of the resultant, or the third vector in the equal sign there.